Benzylic halogenation. In a benzylic halogenation reaction, a benzylic hydrogen is replaced with a halogen. Like with allylic halogenation, what we're going to see most often is that we will be adding a bromine. So we first need to make sure that we know what the benzylic position is. And so you might think from the name benzylic, it sounds a bit like benzene, and we do have a benzene ring. And so the benzylic position is the carbon atom that is attached directly to a benzene ring. So a carbon like this, and it can be a longer carbon chain than just one carbon. I just drew one carbon for simplicity. This is the benzylic position. And what makes it more reactive than other sp3 hybridized carbon atoms is that the reactive intermediates that you form here, so something like a radical, as we will use in this reaction, or a carbocation, as you will see in other reactions, either radicals or carbocations that form at the benzylic carbon are resonance stabilized by the ring, which helps to make them more reactive. And so if we're looking to do a benzylic halogenation reaction, we need a source of a halogen. So quite often we will use the same reagent that we saw for allylic halogenation. So we could use that NBS, that N-bromosuccinimide. So I'll draw the structure here. So that's NBS. And we need something to initiate the radical reaction, so something like light or heat. And this will allow us to replace one of those benzylic hydrogens with a bromine. So in this case, we would end up with benzyl bromide as the product. And this will still work if we have a longer carbon chain, just as long as we have a hydrogen atom that can be replaced, because we see it is a hydrogen that's being replaced with a halogen. So let's take a look at this mechanism. So what the NBS does in this solution is it provides low concentrations, so low concentration of a few different reactive intermediates that we might see, a bromine radical, a little bit of HBr, and also some Br2. And so none of these will be present in a great amount, but enough of an amount that it can do the reaction and then keep the chain reaction going, because radical reactions are always chain reactions. You have only a small amount of radical in your solution at any given time. So let's assume that we have generated a little bit of bromine radical from the NBS. And the very first step that would do that would be the cleavage of that weak nitrogen-bromine bond. So if that bond has cleaved, then we will have a little bit of bromine radical. And it'll be that bromine radical that's going to react with one of these benzylic hydrogens. So if we have a bromine radical, then it can abstract one of these benzylic hydrogens. So it's going to do so by taking one electron of that carbon-hydrogen bond is going to combine with the one electron from bromine. So this is forming a covalent bond, so we're forming HBr, and the other electron from that carbon-bromine bond will go on to the benzylic carbon. So we can see here where that low concentration of HBr is coming from. And so we have a benzylic radical. And so that benzylic radical is resonance stabilized by the benzene ring. So we could draw resonance structures where we show that lone electron on different carbon atoms of the ring. I'm not going to draw them here because although that resonance stabilizes it, we're not going to see any product from any resonance structure other than this one here that we've drawn. This is the major resonance contributor because it has the benzene ring intact. And that benzene ring, that aromatic ring, is quite stable. So once we've got that benzylic radical, it can react with a low concentration of Br2 in solution, and that Br2 is formed by a reaction of this HBr with a little bit of that starting NBS. But again, never in any large quantity at any given time. So if we have this benzylic radical and we have that molecular bromine, then we can show a propagation step that shows us how this radical is combining with one electron from the bromine-bromine bond. So this is indicating that we are forming a carbon-bromine bond. That's what we're looking for. The other electron is going to form more bromine radical that can continue through the chain reaction. And so that is how we can replace a hydrogen at the benzylic position with a bromine. And of course, this now allows us to do further chemistry at this position, because once we have this alkyl bromide, we can think about doing maybe some substitution type reactions. Okay. This reaction here, one last thing I want to say, although we showed this with NBS, we could also use just molecular bromine in this reaction as the source of bromine radical. Right, so we could also use basically the same conditions that we see for a radical halogenation of an alkane. So of an alkane. So we can use those same conditions. We could not do that for allylic halogenation because the pi bond itself might react with the Br2. Here with a benzene ring, we don't usually see the benzene react with Br2 unless it's a very activated benzene ring or we have an additional catalyst in there.